Hey everybody, Trey here. Welcome back to another video. Back with another case study today, and we are going to dive into the most recent official EF-5 tornado in the United States, and that of course is the Moore, Oklahoma EF-5 from back on May 20th, 2013. This tornado tore a 14-mile long path right through the heart of Moore, crossing the path of the May 3rd, 1999 EF-5 and claiming 24 lives in the process. At first glance, the background environment did not really appear to support violent tornadoes, but in this video we're going to take a closer look at why we were able to get an EF-5 tornado out of this setup, as well as some of the interesting behaviors that this supercell and tornado exhibited. So, without further ado, let's go ahead and get started. This has been a very highly requested case study, so hopefully you all enjoy. There's been quite a bit of research done on the Moore tornado and its parent supercell. As always, I'm going to put a link to any website or journal article I mention in the description box below so that you can do some research on your own. May 20th, 2013 featured a moderate risk that was first outlined in the initial Day 2 outlook that you see here, and that really didn't change a whole lot throughout the event. The moderate risk area stretched from far north Texas into central and northeast Oklahoma, extending into southern Missouri and northwest Arkansas. The threat for significant tornadoes existed within the 10% hatched area there, which encompassed mostly the Oklahoma portion of the moderate risk, stretching a little bit farther into southwest Missouri and northwest Arkansas, along with a damaging wind and a large hail threat. 45% areas outlined for each, with a large hatched area denoting the significant hail threat with this setup. Alright, let's dive into the meteorology behind this event. We'll start out at 500 millibars, as we always do, and we'll start out at 12Z, 7 a.m. Central Daylight Time on May 20th. The main feature that catches your attention is this large, high-amplitude, somewhat positively tilted trough centered over the northern plains, extending all the way down into the desert southwest. The center of the trough would just kind of meander across the northern plains during the day. As we've discussed many times before, your most notable significant tornado events are often associated with more negatively tilted troughs, as they have a bit better kinematics and dynamics that favor widespread and intense severe weather. But just because you have a positively tilted trough does not mean that you won't see robust severe weather. We still have favorable large-scale forcing for ascent over a broad area, as well as a strong belt of flow associated with this trough. More specifically, we appear to have a large 60 to 70 knot jet streak embedded within the belt of flow. Now, we've also discussed before how the exit region of a trough or jet streak, if we were to break this jet streak up into quadrants, but particularly the left exit region, is associated with the best spin, the most divergence aloft, the most forcing for ascent within a trough. But there's actually another quadrant that is quite favorable for that rising motion needed to initiate convection in a given environment, and that is the right entrance region. I won't go too deep into the math and physics behind why this is the case, but this animation does a good job of illustrating how this happens. So as we said, we can split up a jet streak into 4 different quadrants using the center axis as that sort of center line. And assuming our flow is generally from west to east, your 4 quadrants are the left exit region, which would be in the top right of this image. In the bottom right, we'd have our right exit region. In the bottom left, we'd have our right entrance region. And in the top left, we'd have our left entrance region. The gray boxes represent parcels of air moving through the jet streak, and if we focus our attention on these bottom 2 here, which are moving through the right entrance region of this idealized jet streak, you'll see as I play the animation how they spread apart from one another. That is upper level divergence, so the spreading apart of the winds in the upper portion of the atmosphere. As we've talked about before, that creates a void that the atmosphere tries to fill by lowering surface pressures and inducing rising motion, which is favorable for storm formation. This occurs in the left exit region and the right entrance region of a jet streak. And if we go back to our 500 millibar map on May 20th, we are clearly in that right entrance region of the jet streak. The exit region is all the way up here from the Midwest into the Great Lakes states, and the right entrance region sits squarely over central Oklahoma. Now, this isn't a super common setup for severe weather, but sometimes due to the geometry and progression of the trough and jet streak, the entrance region can overlap other favorable ingredients, such as low-level moisture, for a robust severe threat there. Not to mention, we also had a very clear shortwave trough embedded within the flow. You can see the kink there in the height contours across northern New Mexico. This would move into the vicinity of the Texas Panhandle by early to mid-afternoon, helping to initiate storms out ahead of it across central and southern Oklahoma. Let's go down to the surface now, and given that the main portion of the upper level wave was situated across the northern plains, we'd expect to see the most robust low-level response in that region as well, and that's exactly what we see here. Very strong, compact, tightly wound surface low situated across South Dakota. Cold front draped down to the south through this little pressure tongue here all the way into the southern plains, linking up with a weaker secondary surface low here in northwest Texas. And as we went into the afternoon, these pertinent features really didn't make a whole lot of forward progress given the slow forward speed of the main upper wave. Now, if you follow the channel for any length of time, you may find this setup somewhat familiar, and you'd be correct. We actually talked about this kind of setup before in our case study on the Joplin tornado from 2011, also discussed in this paper by meteorologist John Davies, written on the Joplin event. If we go to his figure 13, which you see on the right here, we see a schematic diagram of this setup, which he found to be fairly common and often associated with significant severe weather events in the southern plains, including the Joplin event and the El Reno tornado on May 31st, 2013, which you see in his table 1 here. Basically, you have your primary surface low situated off to the north across the northern plains, a cold front draped down to the south and southwest that links up with a secondary surface low or triple point, which is an intersection between the cold front and the dry line, in the southern plains, and ahead of that secondary surface low or triple point is a favored area for significant severe weather, including tornadoes. So this was certainly a setup we'd seen before and one that had been associated with significant tornadoes in the past. Now let's take a look at our raw surface data so we can really pinpoint the locations of these surface features in the southern plains. So we start off the day with very rich low-level moisture across Oklahoma and North Texas, dew points generally in the mid to upper 60s, and they would continue to increase thanks to persistent moisture advection and the strengthening of that low-level southerly flow going into the afternoon. If you watch the dew point at Oklahoma City, we start off the day at 66 degrees at 12Z, 7 a.m. Central Daylight Time, and that would gradually increase into the low 70s by early afternoon, up to 72 degrees by 2 p.m. We can also easily pick out our surface features by this time. Again, we're looking at the surface map at 19Z, 2 p.m. Central Daylight Time. Our cold front is situated across southeast Kansas into west central and southwest Oklahoma. This is evidenced by a clear wind shift across the boundary, winds with a significant northerly component on the west side of the boundary, southerly winds on the east side. We also see a secondary wind shift just ahead of the cold front in Oklahoma. Westerly winds here at Fort Sill on the west side of the boundary, southerly winds across southern Oklahoma on the east side, and we also see a clear moisture gradient along this secondary wind shift, dew points in the 30s, 40s, and 50s on the west side, upper 60s to low 70s on the east side. So this is our dry line, and it intersects the cold front just west of the Oklahoma City metro area, which would be considered our triple point. Oftentimes, the triple point is a favored location for storm initiation in severe weather events because you have enhanced convergence at that point of intersection between the two boundaries. We also see a bit of a dry line bulge just southwest of the Oklahoma City metro area. You can really see how that dry line bows outward in that location. The area ahead of a dry line bulge is also a favored location for storm initiation because you'll see enhanced convergence along the dry line at that point. So all signs were pointing to the area just southwest and west of the OKC metro as the favored location for storm initiation in this environment. Given enough forcing, we also likely see additional development to the south along the dry line, but just by looking at the surface map, you can see that the confluence of ingredients, specifically that triple point and dry line bulge, appeared to be coming together near the OKC metro. Now, I've also heard a theory from a lot of fellow chasers that the Moore supercell was influenced by an outflow boundary from the previous day's convection. But after doing some digging, I really can't find any evidence of a boundary in central Oklahoma on May 20th, of course, other than the cold front and dry line. Here's some radar imagery from the previous day, May 19th, when some significant tornadic supercells occurred along the dry line in central Oklahoma, including one that produced an EF-4 tornado near the town of Shawnee, just east of the OKC metro. As we go into the night, those storms dissipate and new, more linear development takes place across northeast Oklahoma, associated with the tail end of a squall line stretching through Kansas and Missouri, and that would continue into the early morning hours on May 20th. We can clearly pick out the outflow boundary from these storms, this fine line right out ahead of this complex, and if we were to extrapolate that back out to the west, there's really no way that it could have surged far enough south to impact central Oklahoma, and even if it did, it likely would have retreated northward some during the day on May 20th as those southerly low-level winds picked up. Just for reference, here is Oklahoma City right here, and that boundary at best would probably be 40, 50, 60 miles north of the Oklahoma City metro area, and again, may have retreated northward during the day as those southerly winds picked up. Similarly, I don't see much on satellite that would indicate a boundary in central Oklahoma either. The southern extent of this band of clouds could be that outflow boundary that we just talked about, but as we play the loop here, it doesn't make much southward progress through the day, and by mid-afternoon we don't really see any east-west oriented cloud lines or streets that would indicate a boundary across central Oklahoma either. If we look back at our surface observations, we don't really see any notable wind shifts or thermal gradients outside of the cold front and dry line as well. Fairly uniform southerly flow across the warm sector in Oklahoma, And there are really no zones of notable temperature change either. We see 82, 84, 86, 86, so really nothing that would stand out as far as a strong thermal gradient across a given boundary. No wind shifts as well, so it doesn't appear to me that there was an outflow boundary in play on this day. There were many other more important factors at work on May 20th that helped the Moore supercell become a violent tornado producer, and we'll continue to get into these here in a bit. Taking a quick look at our 850 millibar map, we did not have a super robust low-level jet in place for this event. Even up north near the main low-level cyclone, we only have about 30 to 35 knots at most during the afternoon, which is somewhat surprising given the main low-level mass response should be focused up there with such a strong low-level cyclone. And down in Oklahoma, not much improvement. Only about 25 to 30 knots of flow out of the south-southwest at 850 millibars. Now, as we know, this is definitely on the weaker side for typical significant tornado events where we can see low-level jets with upwards of 40, 50, 60 plus knots of flow. This is going to become important in a little bit, so keep this in mind moving forward. All right, let's take a look at a couple of observed soundings to get at least a cursory assessment of the environment. We'll go through our full progression of wrap proximity soundings in just a little bit. These are two observed soundings taken by the NWS office at Norman, Oklahoma at 12Z, 7 a.m. and 18Z, 1 p.m. on May 20th. We start out the day with quite a bit of elevated instability in place, over 2,300 joules per kilogram of mixed layer CAPE at 7 a.m. That is quite a bit for that early in the morning, and it was thanks in part to this deep layer of steep lapse rates extending all the way up to about 500 millibars. This was a very well-defined elevated mixed layer, or EML, that layer of warm, dry, well-mixed air that emanates from the higher terrain of the desert southwest and western Mexico, and gets transported into the plains atop the low-level moist layer. Speaking of that moist layer, it was somewhat shallow to start the day, only extending up to about 900 millibars, up to that very stout cap associated with the elevated mixed layer. Lots of warm advection ongoing at this time as well, evidenced by the large looping low-level photographs and the nicely veering low-level winds with height. Fast forward to 18Z and some significant changes had taken place. The moist layer had deepened substantially thanks to persistent low-level warm moist advection. You can see it extends up above 850 millibars by this time, and the cap was quickly eroding. The combination of favorable synoptic scale ascent within the right entrance region of the main jet streak and ahead of that shortwave trough was helping to efficiently lift and cool the capping inversion. It would only take a couple more hours of continued large-scale ascent and surface heating and moistening to fully break the cap and allow storms to fire. This is your classic loaded gun type sounding. As for the wind profile, it's not one at first glance that you typically associate with violent tornadoes. There is some modest veering and strengthening of the low-level winds with height, leading to some modest hodograph curvature in the low levels, about 160 meters squared per second squared of effective storm relative velocity. Certainly adequate for tornadoes in right-moving supercells, especially given the thermodynamic environment, but generally not super favorable for significant tornadoes without some other mechanisms at play. Still, strong deep layer shear for supercells, effective bulk shear over 50 knots, and those supercells would tend to be at least semi-discrete given deep layer shear vectors fairly perpendicular to the dry line, especially across central and southern Oklahoma. So to summarize this environment, we definitely had the forcing mechanisms in place to initiate supercells along the dry line. Quite an explosive environment given very strong instability and a quickly eroding cap, but the wind profile was not necessarily super favorable for strong to violent tornadoes. Large to very large hail certainly seemed like a notable threat given strong instability, especially in the hail growth zone, and somewhat muted low-level shear, but it certainly didn't seem like an environment that might spawn an EF-5 tornado. Perhaps a few tornadoes with supercells along the dry line, but definitely not a strong to violent tornado like the one we saw in Moore. Storms initially fired along the dry line east of Lawton, Oklahoma just before 1 p.m. and would quickly increase in both coverage and intensity, including additional development to the north and south of the initial storms. You can easily pick out the cold front and dry line on radar with that triple point setting up just west of the Oklahoma City metro area. Now let's zoom in on this northern area of storms as the Moore supercell would emanate from this convection. We'll begin this animation just after 19Z, 2 p.m. We have a few little spuds that develop ahead of the triple point near Tuttle and Bridge Creek. They quickly intensify and take on that classic supercell shape. Precipitation vented off to the east-northeast, well-defined appendage on the southwestern flank of the storm. And this was especially well-defined on the southernmost storm of the bunch. Now I want you to focus on this blip just west of the developing hook echo. This was a small cell that initiated just west of the flanking line of the southernmost supercell, and it's a little tough to tell on these images, but there was actually another small cell that developed in this area just west of the supercell's flanking line, and these two tiny cells eventually merged together, creating a single new cell. And you'll notice over the next few scans that this new cell eventually merges with the hook echo. This merger appears to have initiated a surge in the rear flank downdraft. You'll see the tip of the hook really start wrapping around at this time. This is at 1951 Z, about 5 minutes before tornado genesis. And if we pull up the velocity data, you'll see a corresponding increase in inbounds, winds going toward the radar, which are the greens here. Reds are going away from the radar. And this strengthening of those inbounds represents a significant strengthening of the RFD, which initiated tornado genesis in this supercell. We see a corresponding increase in inflow into the mesocyclone as well. The mesocyclone tightens, and we get a tornado to develop just a few seconds after this image. This merger also initiated something called a descending reflectivity core, or DRC. A descending reflectivity core, as described in this paper by Rasmussen et al. 2006, is an area of precipitation aloft that protrudes outward from the echo overhang on the rear side of the weak echo region. So in simpler terms, it's a blob of precipitation that descends within the right rear flank of the storm and often leads to the development or intensification of reflectivity in the hook echo. Numerous studies on DRCs, including this paper by Rasmussen et al., Biko et al. 2009, and the SPC paper on the Moore supercell led by SPC meteorologist Chris Broyles, have shown that DRCs are often a precursor to tornado genesis because they infuse stronger flow into the rear flank downdraft at ground level, yielding an increase in vertical vorticity or spin. They also appear to shelter the incipient tornadic circulation so that it can organize vertical vorticity without being destroyed by low-level shear. Now, DRCs can be somewhat difficult to ascertain using just normal 2D radar, but if we look at a vertical cross-section of the Moore supercell, we can see the DRC associated with this initial merger. And for that, we will use the video narrated by Chris Broyles that describes the tornado genesis process within the Moore supercell, which is in concert with the aforementioned SPC publication. Again, all of these links to these resources are going to be in the description box below. Here we are at 1942 Z, about 13 minutes before the tornado begins. The merger between that ancillary cell just west of the supercell's flanking line and the hook echo of the supercell has taken place, and this initiates a DRC, which is this small area of enhanced reflectivity right there, protruding outward from this area, which is the echo overhang that we talked about when we defined what a DRC is. You can see it's on the back side of the weak echo region right there, which is associated with the strong rotating updraft or mesocyclone of the supercell. It continues to descend over the next several minutes until it reaches the ground at about 1959 Z, helping to organize the vertical vorticity and consummate the tornado genesis process. Not every supercell features a DRC, but those that do have been found to more easily undergo tornado genesis for the aforementioned reasons, and the Moore supercell certainly appears to fit the bill. So by this point, about 1956 Z, the tornado was in progress. Classic supercell shape with a very pronounced hook echo as that RFD began to surge and wrap around the mesocyclone. Looking to the south of the developing tornado, we see yet another small storm making its way up toward the Moore supercell. This cell would merge with the mesocyclone region of the main supercell and initiate yet another descending reflectivity core. So in this vertical cross-section, we're looking southwest through the forward flank of the storm toward the supercell's hook echo. Here is that cell moving up from the south. As it begins to merge with the hook echo, it initiates a second DRC, which is this area of slightly enhanced reflectivity right there. It continues to descend and wrap around the ongoing tornado, and this had major implications on the size and intensity of the mesocyclone. Going back to the velocity data starting at about 1956 Z, the tornado begins here, northwest of Newcastle, and between 2008 and 2016 Z, you can see, especially in the outbound winds, the reds here, how the mesocyclone expands and then quickly contracts as the tornado enters the west side of Moore. At 2008 Z, the DRC was still in the process of wrapping around the low-level mesocyclone, and thus the mesocyclone expands. You can see how the inbound winds, those red pixels there, within the mesocyclone almost double in size from 2008 to 2012 Z. This was likely in an attempt to continue to concentrate the additional vertical vorticity from the DRC. By 2012 and beyond, that process is completed and the DRC is fully engulfed into the tornado, and the mesocyclone constricts significantly as it enters the west side of Moore. We can see this clearly in the damage survey from NWS Norman. As the tornado crosses I-44, it expands in size, and then it quickly constricts as it enters South OKC and West Moore, at which point the main swath of EF-4 and EF-5 damage occurred. Just like a skater brings his or her arms inward to spin faster, the constriction of the low-level mesocyclone was coincident with the intensification of the tornado, and a major disaster was on our hands as Moore sat right in the path of this violent tornado. The tornado continued on through Moore, producing extensive EF-4 damage with small areas of EF-5 damage at Briarwood Elementary and near the Moore Medical Center. We see a very well-defined area of intense reflectivity at the tip of the hook, which is a clear debris ball, indicating lots of debris being lofted by the tornado. The tornado remained in progress for about 40 minutes before finally dissipating just west of the KTLX radar site at about 2036 Z or 3:36 p.m. We can get an even closer look at the intricacies of the tornado by using data from the PX-1000 radar, which is a super high-resolution polarimetric research radar from the University of Oklahoma that was located at the Max Westheimer Airport in North Norman on May 20th, only about 6 to 6.5 miles south of the tornado track as it passed through Moore. I'll put a link to this animation in the description below, as this is some of the highest resolution, closest range data of a violent tornado you'll ever see. On the top left is reflectivity, top right is velocity, bottom left is differential reflectivity, and the bottom right is correlation coefficient. As a quick refresher, correlation coefficient is a measure of how similar the objects are that the radar beam bounces off of. If the radar beam bounces off of only similarly sized raindrops, then the correlation coefficient will be near 1. But when the radar bounces off of raindrops along with debris, boards, bricks, nails, branches, etc., lofted by a tornado, that correlation coefficient drops significantly, and when a concentrated drop in correlation coefficient occurs in the same spot as a tornado vortex signature, that's how we can confirm the presence of a tornado based solely on radar. So we'll start just after 1956 Z as the tornado begins. We see a well-defined velocity couplet in concert with a notable feature in reflectivity that we call the weak echo hole, right at the center of the circulation. We've talked about these before in our Greensburg case study. Very similar to the eye of a hurricane, the weak echo hole is a region of low reflectivity coincident with the tornado vortex that is surrounded by higher reflectivity, and it's generally caused by the centrifuging of hydrometeors outward from the center of circulation. There have been numerous past tornado cases, many of which have been strong, where weak echo holes have been documented, mostly by mobile radars, and the Moore tornado here exhibited a very well-defined one. We continue on, and within the first few minutes of the tornado's life cycle, it strengthened quite rapidly, and by about 20 Z on the nose, a well-defined drop in correlation coefficient occurred, coincident with the strengthening tornado vortex signature in velocity data, signaling the presence of lofted debris. The tornado vortex signature continued to intensify over the next several minutes as that second DRC began to interact with the mesocyclone, and here's when things get really interesting, particularly with the characteristics of the tornado debris signature. We start to get numerous instances of what we call debris ejections. This is basically when you get these ribbons of lowered correlation coefficient that get shunted away from the main debris signature, and they're directly related to surges in the rear flank downdraft, which is quite intuitive. You get a strong push of RFD, that's going to propel a bunch of debris outward from the main circulation. And these debris ejections happen repeatedly after about 2014 Z. You just see one after another these ribbons of lowered correlation coefficient spiraling outward from the main debris signature, and you can even see slightly enhanced inbounds, in this case the green velocity pixels, surging southward and eastward coincident with these ejections. Each of these debris ejections is documented in depth in Kurdzo et al. 2015. They identified at least 8 different RFD surges, most of which were accompanied by a debris ejection. They also noted slight shifts in the tornado track associated with many of these RFD surges, as you see in their figure 9 here. Each dashed circle represents an RFD surge, and you can clearly see some slight shifts to the track in concert with many of these RFD surges, including this loop that occurred near the Moore Medical Center. But there was a little bit more at play to cause such a robust alteration to the track. This loop occurred between 2021 and 2023 Z. Up to this point, we had seen a fairly steady-state significant tornado, again with some slight track alterations due to those RFD surges, but in general a steady-state vortex. Leading up to this loop, the velocity couplet was extremely strong, with delta V values upwards of 125 meters per second, which is nearly 280 miles per hour. We then see a drastic weakening in the intensity of the vortex and a significant slowdown in its forward speed. Delta V drops to about 75 meters per second, or about 170 miles per hour as the loop begins. Now, there were some changes in the storm's structure leading up to this loop. At around 2016 Z, the tornado was fairly steady state, producing EF-5 damage near Briarwood Elementary. Now let's focus on the differential reflectivity field in the bottom left over the next few minutes. As a quick note, differential reflectivity, or ZDR, is a product that allows us to determine the dimensions and orientation of the objects that the radar beam bounces off of. Positive ZDR indicates targets that are larger in the horizontal than the vertical, and the opposite is true for negative ZDR. So at about 2016 Z, we see a band of lowered ZDR on the southern flank or inflow-facing side of the supercell's precipitation core relative to the remainder of the core, which features much higher ZDR. This is called a ZDR arc, and these are present in a good percentage of right-moving supercells. According to Kumjian and Rizkov 2008, they result from strong wind shear which allows smaller raindrops with higher ZDR and that fall more slowly to be transported farther from their source region, relegating mostly larger raindrops to the southern edge of the forward flank. So you see here these greens are indicative of lowered ZDR. So your larger raindrops, which are not subjected as long to the strong wind shear, they are allowed to collect on the southern flank of the forward flank precipitation core, while these smaller drops are vented off to the north and northeast thanks to the strong wind shear in place. Now watch what happens over the next few minutes. The ZDR arc redevelops to the west-southwest of where it was previously. Kumjian et al. 2010 hypothesized that this westward transition of the ZDR arc indicates a disruption to the updraft and the beginning of the occlusion process, where the RFD gust front begins to fully wrap around the mesocyclone and cut off the circulation from the warm, moist inflow that it needs to sustain. At the same time, an area of lowered correlation coefficient began to develop on the southern flank of the precipitation core, possibly signaling debris fallout. Then around 22Z, we see an RFD surge and debris ejection mostly toward the east and northeast, which differed from the others, which were toward the south or southeast. You see this band of lowered correlation coefficient extending out to the east and northeast from the main debris signature, which had been different from most of the other RFD surges and debris ejections, which had been toward the south and southeast. This is a common occurrence during the occlusion process of cyclic supercells. So it's quite clear that the Moore tornado underwent a failed occlusion, similar to the El Reno tornado in 2013, and we talked about this in our case study on that event, that sometimes tornadoes will attempt to fully occlude, which often involves them moving toward the north or northwest, but the supercell, for whatever reason, cannot consummate that process, so the tornado loops around and eventually resumes its original direction and speed of motion. Unfortunately, the Moore tornado's very slow forward speed during this loop allowed the area near the Moore Medical Center to be subjected to the intense winds of the tornado for much longer, leading to the second area of EF-5 damage within the damage path in that location. Alright, let's dive into our progression of RAP model soundings in proximity to the Moore supercell, because we still haven't really figured out the key to why this environment, which on the surface did not appear to be super favorable for strong to violent tornadoes, was able to produce the Moore EF-5. If you enjoyed all that discussion about the storm's behavior, be sure to check out the articles in the description box below, as they go even further in depth on these unique storm and tornado scale processes. So these soundings were taken from Max Westheimer Airport on the north side of Norman, Oklahoma, again about 6 to 6.5 miles south of the track of the tornado as it went through Moore. At 12Z, we start out the day, as we discussed, with a strongly unstable but strongly capped environment, thanks to that deep elevated mix layer extending up to almost 500 millibars. Also, warm advection ongoing in the low levels, given veering and strengthening winds with height, strongly curved hodographs to start the day. As we go through the morning into the early afternoon hours, we can see the impacts of the large-scale forcing for ascent from being in that right entrance region of the main trough and the incoming shortwave. That cap is efficiently lifted and cooled, the moist layer deepens, and we've primed the environment from a thermodynamic perspective. And by 17 to 18Z, 12 to 1 p.m., we're fully uncapped with strong instability in place, nearly 4,000 joules per kilogram of mixed layer CAPE by 19Z, 2 p.m. So the thermodynamic environment definitely supported explosive convection. The wind profile, on the other hand, left something to be desired as far as tornadoes go. We'd lost some of that hodograph curvature from earlier on in the day. Winds in the lowest couple kilometers of the atmosphere were somewhat muted, with limited veering with height, leading to fairly mediocre hodographs. The limited low-level shear certainly appeared to support large hail, especially given the strong instability. And that was the main hazard with most of the storms along the dry line in Oklahoma. We can see a clear dichotomy between the storms to the south with a bunch of hail reports and really no tornado reports, whereas to the north there really aren't many hail reports, just the few tornado reports from the Moore supercell. So there had to be some sort of localized enhancement in low-level shear farther to the north, and Broyles et al. Were able to identify something that may have done the trick. If you recall from our radar analysis, we identified a small storm that merged with the Moore supercell as it was organizing and initiated a second descending reflectivity core. Broyles et al. Found that winds associated with this storm at about 700 millibars were around 60 to 75 knots, which was 20 to 25 knots greater than what the proximity and observed sounding suggested. We had another small storm fire up a bit later and take a similar path, and winds at 700 millibars associated with this storm were only about 45 to 55 knots, which is about the same as the proximity and observed soundings. Broyles et al. Looked at vertical cross-sections of velocity data and determined that the increase in 700 millibar flow around the time that the Moore supercell was organizing was due to a very small-scale, localized mid-level jet streak. Here's that vertical cross-section beginning at 1934Z, so about 20 minutes before the tornado began. Here's the developing mesocyclone of the Moore supercell, And here is that little cell to the southwest. You can see the blue colors there. That is indicative of enhanced flow of about 60 to 75 knots at 10 to 20,000 feet. This is the nose of that small-scale 700 millibar jet. It continues to approach the Moore storm and finally interacts with the mesocyclone at about 1947 Z, around 9 minutes before the tornado would begin. The strong winds from the jet then began to mix downward. You can see the extensive area of those light blues there seeping below 10,000 feet, which helped to strengthen low-level flow and reinforce the initial RFD surge, allowing the mesocyclone to strengthen rapidly. The localized jet continues to impact the Moore supercell for quite a while until about 2021 Z, when we see those low-level winds decrease suddenly, returning back to levels exhibited on the nearby sounding of about 45 to 55 knots. Interestingly, this is around the time that loop in the track and the associated failed occlusion happened, so it's likely that the short-lived boost to the wind profile aided in significant tornadogenesis and intensification during the time that the jet streak was impacting the storm, and then once the jet passed, the wind profile became less favorable, the storm tried to occlude and generally weakened from that point onward. Just how big was this boost to the wind profile? Well, Broyles et al. Modified the 18Z observed Norman sounding to reflect the passage of this localized jet streak and the associated mixing of stronger flow downward into the low levels. Here is the actual Norman 18Z sounding. The photograph, as we said, exhibits very limited low-level curvature and modest effective storm relative velocity of about 150 meters squared per second squared. Here is the modified sounding with changes made to the wind profile as shown here in the bottom right. And we can see what happens to the photograph. We go from a wind profile that seems generally unfavorable for significant tornadoes given somewhat muted low-level shear to one that is vastly enlarged, massive low-level curvature, ample streamwise vorticity, and effective storm relative velocity over 400 meters squared per second squared. Clearly a wind profile that favors significant tornadoes. So this small-scale mid-level jet streak likely had an enormous impact on the wind profile. It was extremely small, only about 30 miles long by 8 miles wide, as estimated in the Broyles paper, so any normal data source, such as the SPC mesoanalysis page, would not be able to resolve something on this small of a scale. And it was not large enough to impact the environment farther south, where wind profiles remain generally unfavorable for tornadoes, let alone significant tornadoes. It was only able to impact the Moore supercell, and its effects were drastic. So that's going to do it for this video. There's a lot more we could have dived into regarding this historic storm, but hopefully this provided a solid overview of how this EF-5 tornado happened in an environment that on the surface didn't necessarily support significant tornadoes. Again, I encourage you to take a look at the articles in the description box below as they go even further into depth into some of the things we talked about and lots more. This was certainly a unique storm that produced an absolute monster, and the scars still remain across parts of Moore, but these folks have come back strong, and hopefully we can learn from this event in the future to better prepare for when this happens again. So that's going to do it. Thanks for watching, and we'll see you in the next video.